Hello, my name is Sean Argyle, and I'm a math teacher at Warrensville Heights High School, and I hold my PhD in Curriculum and Instruction from Kent State University, and this is my presentation entitled Mathematical Thinking from Cacophony to Consensus, which will be presented at the 2013 Joint Mathematics Meetings in San Diego. The first question you're probably asking yourself is, why is a high school math teacher presenting in a philosophy of mathematics session? Well, the answer to that question is that I believe mathematics education is a sort of applied philosophy of mathematics. For example, a math teacher asks, how do I get people to learn mathematics? And that's a question of epistemology. Or, how do I break mathematics into comprehensible chunks? And that's a question of ontology. Or, what experiences are necessary in order to learn mathematics in the first place? And that's a question of phenomenology. All of these are issues of philosophy of mathematics, simply set in a real-world context. The call for proposals for this session talked about standing on the shoulder of giants and how that's something that we're supposed to be doing as mathematicians and philosophers of mathematics. However, the call for proposals also made it clear that this wasn't always the case. In mathematics education, we have a similar problem. Here you see a quote talking about how researchers in mathematics education use the phrase mathematical thinking to mean whatever they want it to mean. That doesn't sound like standing on the shoulders of giants to me. There may be giants involved, but there's no standing on shoulders happening whatsoever. When you take a closer look at articles in mathematics education, you begin to see that cross-referencing just doesn't seem to happen at all. I looked at about 180 articles, and of those 180 articles, on average, less than one citation per article had anything to do with the other 180 articles that I looked at. If that's not bad enough, you begin to realize that most of the references that occurred within the group were, for example, Richard Lesh citing Richard Lesh, or people in a special issue who knew who else was going to be published with them. They didn't really cross-reference each other, just said, there's also this article in the same issue that you can turn to page 17 and read about. Really no cross-referencing whatsoever. Here's a case in point. Both Bonato 2005 and Rasmussen, Zendaya, King, and Teppo 2005 were talking about this word mathematization. And as you can see here, they both had elements of horizontal mathematization and vertical mathematization. But Bonato considered organization to be an aspect of vertical mathematization, whereas Rasmussen, Zendaya, King, and Teppo thought organization was the horizontal mathematization. Clearly, these two were not keeping in touch with how the other person was using the words. But the chaos doesn't stop there. David Tall in 1992 had a two-step cyclical model of mathematical thinking. Concept image, concept definition, concept image, concept definition, back and forth, back and forth. A decade later, in 2004, he says, no cycle, it's a linear model, starting from this physical world to this abstract world. 3 steps, linear, as opposed to 2 steps, cyclical. So it wasn't simply an evolution of his idea of mathematical thinking. He completely started over from scratch. At this point, I'm totally drowning in the cacophony of different definitions for mathematical thinking. What am I going to do? Which one do I pick? I don't know. And then I took a step back and thought about my undergraduate philosophy of natural science class. Thomas Kuhn had this system where you start with normal science and you go to revolutionary science. You do normal science, you get a few anomalies, a few more anomalies, a few more anomalies, and finally you can't explain the anomalies anymore and you have a revolution, a paradigm shift as he would call it. But before any of that happens, he has pre-science. Kuhn defines the pre-science period as when people have to reinvent the wheel, that is, start over from scratch and never rely on the work of what people have done before. That's exactly what was described as happening by Selden and Selden and in the call for proposals. I said, aha, here we are in pre-science. That's why we are having problems. So at this point, I had a new question. Not what is mathematical thinking, but what's keeping the experts from reaching an agreement? That was a new question and a question of philosophy. Option 1, there is no underlying universal process, in which case we should not even be having this discussion, so I couldn't use that. Option 2, the question is fundamentally unanswerable. Just like Wittgenstein used to say, you can't use logic to talk about logic. Perhaps we cannot use mathematical thinking to talk about mathematical thinking. Who knows? Again, why even have this conversation? The only viable solution here is that there is a philosophical barrier to agreement, and that is the assumption that I began to use. In this way, I chose not to use a social science methodology to conduct my research. I actually used a philosophical method called conceptual analysis. In particular, I used John Wilson's thinking with concepts to guide me. The number one phrase that applies, and will help you understand why I picked it, is Wilson says, conceptual analysis is not about looking for the meaning of a word, just like I wasn't looking for the meaning of mathematical thinking. I was looking for the actual and possible uses. That is to say, how are people actually using these words? And from that, perhaps I can intuit the definition. If you'd like to hear some more detail about how I conducted my research, why I chose what articles I did, etc., etc., you can go to another video on my channel and view my dissertation defense proposal and Q&A panel. But for now, just understand that I used conceptual analysis. The end result of my conceptual analysis revealed that there was a hidden consensus once you got past the philosophical barriers. It's rather like the parable of the blind men and the elephant, limited only to a sense of touch. If you stand at the front end, you think the elephant's tusk is a spear, or at the other end, you think the tail is a rope. Being limited only to a sense of touch, that is, myopically only able to conceive a small portion of the greater whole, you don't realize that there's an elephant standing between you. Likewise, once we get past some of the philosophical differences, there's actually a great deal that we can come together and talk about. You just have to get past the fact that you're not talking about two objects, you're talking about one. The first philosophical barrier preventing consensus is an epistemological one. There are two extremes to the spectrum, the Platonist extreme and the formalist extreme. At the Platonist side of the spectrum are Ginsberg and Co., 1999, who talk about mathematics as if it has some sort of reality into itself. If only we had the hands that could reach, there would be a physical reality to mathematics, somewhere outside of human beings. At the other extreme, the formalist side of the argument, Sinclair 2004 says mathematics isn't real in and of itself, it is simply a way that humans organize their experience. At first glance, you would say to yourself, there's no reconciling these two extremes. However, the way people actually talk about mathematics and mathematics education rarely falls 100% into a Platonist category or 100% into a formalist category. Instead, there's a vast array of intermediate beliefs, which led me to say there must be some common ground. My assertion is that the solution here is to take a post-epistemological stance. That is to say, I believe that the question of whether or not mathematics is real has an independent reality outside of humans, and that we come to know it through some sort of abstract means in which we reach into mathematical reality is irrelevant. Even though the formalist position, as embodied here by Sinclair, says the mathematical world isn't real, doesn't reject the existence of a mathematical world. They simply think it is a virtual world, one created by humans and harbored entirely within our own conscious. That is to say, it doesn't matter whether or not it's real, both sides agree that there is a mathematical world. To begin the process of standing on the shoulder of giants, we need to set aside questions of how and where such ideas are stored, and simply acknowledge that they are. We can move forward on that assumption. The second philosophical problem is not one quite so easily resolved. It is an ontological problem in which we try to break down mathematics into reasonable bite-sized chunks. That is to say, what is the quantum of mathematics, the smallest piece of mathematics that makes sense in and of itself. Here you see a comic by Randall Munroe called XKCD, demonstrating the way in which we can consider various disciplines of human thought as lying on a spectrum, not necessarily discrete. On a smaller scale, we can start to ask ourselves the same questions. Geometry, algebra, trigonometry, calculus, statistics, Where do they fall apart? Where does algebra end and geometry begin? I asked myself the question, is statistics part of mathematics? Or, like physics, is it simply applied mathematics? There are arguments both in favor and against the inclusion of statistics as part of mathematics. I had people who went to great lengths to try to distinguish statistical thinking from mathematical thinking. However, once I looked at the things that people called statistical thinking and compared to the things people called mathematical thinking, I realized that they had the same basic, for lack of a better word, shape. They had the same component parts. The only differences were emphases and basic underlying assumptions. And in the case of differentiating between statistics and mathematics, it comes down to very fuzzy decision-making about whether or not inference and induction count. And I'm not talking mathematical induction, I'm talking about inductive reasoning in general. So if the question is statistics mathematics, the answer depends on what you really want to call mathematics. And the same can be true of physics and chemistry and biology. It becomes a very difficult to navigate quagmire that was beyond the scope of my research at the time. The end result of my conceptual analysis is presented here. However, I'm not going to take the time to discuss it. If you're interested in learning more about this, you can view my other videos in this channel about my dissertation. Just to give you a brief taste, here's one way I can use this in the classroom. There's a common misconception that students have that multiplying makes things bigger. Using my model, here are 4 different ways that I can explain where that behavior comes from. The first route is through normalization, that is, deferring to certain cultural norms and expectations. I can certainly think back to my math teacher saying, multiplication is repeated addition, multiplication is repeated addition, multiplication is repeated addition. So many times that I said, oh, that must be the case. I deferred to their authority. It's a simple matter to say, well, addition is more, so multiplication is also more. Okay, no problem. Likewise, it's easy to imagine a student who continues to get such easy worksheets that they never experience the case where a fraction or decimal is involved to make multiplication involve making smaller. In this scenario, they lack the basic fundamental experience to abstract that it could do anything other than make bigger. At the opposite extreme of experience, you may have a gifted student who justifies the belief that multiplying makes bigger through a complicated wheedling process in which they say, oh no, a fraction multiplication, there's not anything making smaller. A over B really means A divided by B. And so the A times C is still making bigger, it's the division by B that makes smaller, and so multiplication makes bigger. And let's not forget that the word multiply has a definition outside of the mathematical context. In plain English, multiply means duplicate. Rabbits multiply. That means there's more rabbits. Okay, multiplying makes more, multiplying makes bigger. This intuition based upon real world can interfere with the mathematical thinking. To bring things full circle, let us recall that I began this presentation by talking about how a mathematics educator is a valuable member of the philosophy of mathematics conversation. The last few things I want to talk about are aspects of the philosophy of mathematics based upon my actual classroom experience examining and trying to understand the mathematical thinking, or more specifically, the lack of mathematical thinking in real-life students. The first thing I did this year is asked, who is a mathematician? And my students were confused. They clearly hadn't spent a whole lot of time thinking about it and responded with the off-the-cuff answer, someone who is good at or likes math, such as an accountant. After pestering them for multiple days, I finally was able to get them to say, someone who solves problems and creates things, usually science, by using math. Parents, rappers, and even President Obama made the list of people who are mathematicians in the eyes of students. Considering that mathematics is not entirely a solitary discipline, that is to say, one must interact with some sort of community, the fact that they're not really sure who is a member of that mathematical community is a real problem for philosophy of mathematics. How do we decide? Who decides? That's something that I couldn't answer right now. Maybe one of you will someday. As I mentioned earlier, the boundaries of mathematical thinking are very fuzzy, and I don't know where exactly they start or end. I asked my students, who can be a president? And their short memory said Obama and Bush. And I said, what kind of money is there out there? They said dollars, and a few of my smarter students said pounds. And I said, well, is there any overlap? And the kid really squinched his eyes and closed and really thought hard about it. He said, Ben Franklin. Not only is Ben Franklin on the bill, but we actually refer to that denomination as a Ben Franklin. He was clearly doing some heavy thinking, And Venn diagrams and set theory are math. But Ben Franklin, Obama, Bush, dollars, pounds, not so much. Where does the thinking begin? Where does the thinking stop? Where does the mathematical thinking begin? Where does the mathematical thinking stop? I don't know. And more than anything else, really, I struggle with the fact that I'm supposed to be teaching them math, but there are beliefs they have about the world beyond mathematics, outside the scope of mathematics, that strongly influence the way they behave in my classroom and the way that they engage with the classroom. I have no control over my grades. It's shameful to ask for help. If it looks different, it is different, or if it looks the same, it is the same. They have these beliefs about things beyond mathematics that are not about mathematics, yet they clearly influence their beliefs about mathematics, and I have no idea how to control that. How to design a math lesson about things that are not math. For more information about my research, or to get a hold of me, here's some contact information. Thank you so much for viewing this video.